So if you can't remember what we went over yesterday on Thursday, we went over hypothesis testing for dependent data set. So what we're going to do today, we're essentially going to continue on with that trend, and we're going to continue doing hypothesis testing for dependent data set. All right, well, I'll check that later. So for hypothesis testing for dependent data set, so if you remember, dependent data set meaning like the data set is like a before and after or a match pair. So whenever you have like a before and after or a match pair, you want to use pretty much this technique. So let's go ahead and do this next problem. So it says the 2008 Olympics were full of controversy about new swimsuit possibly providing unfair advantage to swimmer, leading to new international rule that came into effect January 1st, 2010, regarding swimsuit coverage and material. Can a certain swimsuit really make a swimmer faster? A study tested whether wearing a swimsuit influenced the swimming velocity. So the measuring the swimming velocity. So it's a 12 competitive swimmer and triathlete swam 1,500 meters at a maximum speed twice, each once wearing a wetsuit and once wearing a regular bathing suit. The other of the trial was randomized. Each time the maximum velocity is meter per second of the swimmer. These data in the table 3 assume that the data had a normal distribution. All right, so if you kind of read the question said they had 12 swimmers. So here go the 12 swimmer. So they made the swimmer swim twice, one of them with the wetsuit, one of them with a regular wetsuit. So there you say no wetsuit. So if you actually read the question, it said that the swimming velocity was calculated. So they were calculating like how fast they were going. So if they were going faster with a wetsuit, you would expect them to have a bigger number. If they go slower with no wetsuit, you should expect them to have a smaller number because they're collecting the velocity, not the time. So if you look at it, since they measured them before they had the wetsuit and after they were wearing the wetsuit, this is essentially a before and after. So that's why this will be considered a dependent data set. All right. Everybody go why this is a dependent data set. All right. So up next, what we want to do, we're going to calculate the difference. So what I want a positive number, meaning that the wetsuit actually made them go faster. And I want a negative to be that the wetsuit actually went slower. So if I want that, we're going to do wetsuit minus no wetsuit. So if I do wetsuit minus no wetsuit, you should get a positive number if wetsuit is bigger than no wetsuit. If wetsuit minus no wetsuit is equal to a negative, that's wetsuit less than no wetsuit. Everybody so far good with that? All right, sweet. All right. Meaning faster or not faster with the wetsuit? Yeah, correct. Meaning faster or not faster. All right, so I'm going to go ahead and subtract these. So let's go ahead and do this. So this is 0.08, 0.10, 0.07, 0.08, 0.10, 0.11, 0.05, 0.05, 0.06, 0.08, 0.05, and 0.10. All right, so those are the difference. So this is the value we're going to enter into our TI-84. So let's go ahead. Let's go ahead and do this one. So let's do step 2. So it says, in a sentence, describe the parameter that is being tested. The mean difference, difference of the speed velocity with the wetsuit and without. So if you look at what's being tested, so what's being tested, the mean difference of the speed velocity with the wetsuit and without the wetsuit. So we don't want to pretty much say, okay, let's compare them with the wetsuit and compare them with no wetsuit. What we want to do, we want to see what is the difference between wetsuit and no wetsuit. All right. So let's go ahead. Here, let's do the known alternative hypothesis. All right, let's meet some people. All right, so for the null hypothesis, we're going to put mu of d bar is equal to 0. So if you remember for the null hypothesis, we always put mu of d bar is equal to 0 because essentially we're saying there is no difference. So if the difference of the two before and after is 0, that means there's no difference. So that way you say mu of d bar is equal to 0. For my alternative, since I went ahead and did it where a positive, meaning that the wetsuit doesn't make you go faster, you go mu of d bar is greater than 0. Well, because if you look right here, we're taking the difference. So when we're actually doing this problem, we're only going to use this data set over here. We're not going to be using the mean of each individual wetsuit and no wetsuit. What we're going to do, we're going to just use the difference of those two values. So that way the mean difference. All right. All right, so let's do step number 4. So step number 4, just get the n, the degrees of freedom, and the difference. So n in this case is 12, degrees of freedom is 11, and the difference, well, this is my difference. Let me see if I can just get it. Copy. So that's my difference. So up next, what I'm going to go ahead and do, I'm going to go ahead and check my assumption before I forget. So for this one, if you look at it, it's check for assumption. So you have to check for the central limit there. But luckily for us, if you look at the problem tells us assume that the data has a normal distribution. So since we're assuming that the data has a normal distribution, no need to check assumption. So no need to check assumption. Because you only want to check the assumption if our data set is non-normal. But since they already told us our distribution is normal, there's no need to check the normal distribution. Well, to check to see if it's normal. All right. So up next, what I'm going to go ahead and do, we're going to go to TI-84. And we're going to go ahead and do this. So go over here, TI-84. So we go to stats, we go to edit, and we enter this data set. So you go 0.08, 0.10, 0.07, 0.08, 0.10, 0.11. All right, so I enter all the data set here. So what I'm gonna go ahead and do, we're gonna go to stats, we're gonna go to tests, and we're gonna go do the t-test. So anytime you're doing where you're testing dependent data set, you always wanna do the t-test. So for this one, you wanna say you have data. So you put the data right there. And if you remember for mu d bar, we put that is equal to 0. So you leave this at 0. The only thing we have to change is this inequality. We change it to greater than, and then we go ahead and calculate it. So if you look at my t value, you got a pretty high t value. We got a t value of 12.32. Also, if you look right here, they gave us the mean. So this is the mean difference. So that's d bar. So that's 0.0775. And lastly, if you look at S of x, that's the sample standard deviation of the difference. So that's 0.0218. Okay. Also, if you look at it, they gave us p-values. So I'm going to go ahead and just note p-value. So p-value is 0.0. Well, actually, a lot of 0. 2, 3, 4, 5, 6, 7. And you put 4. So if you look at p-value, p-value is 0.00008. Now, I said it for dependent data set. Thank Julian. But yeah, for this one, since it's dependent data set, you use a t-test for this one. All right, so the two major things you should have gotten at that we got t-value equal to 12.31815. You get p-value practically equal to 0. So I'm gonna go ahead and switch over to my notes. All right. So if you look right here, I just enter what is the mean difference, what is the standard deviation of the difference, what is the t-value that we get. I also enter that this is a right tilt test. I enter the p-value. All right, so for this one, what is my alpha level? So if we go up here, if you look at it, say significant level of 5%. So we have a 5% alpha level. So that's 0.05. So which of the two will be bigger, a p-value, which is practically 0, or an alpha, which is 0.05? Yeah, alpha. So we conclude this. So if you look at it, we say reject HO. So we'll say there is enough evidence to say that all right. So for this one, for part 7, we'll put there is enough evidence to say that the mean difference of the velocity with and without the swimsuit is significant. Because if you actually go back and look at the difference, just by looking at the difference, you can kind of tell that it's significant. Because if you look at all of them, all of the people who had the wetsuit versus when they didn't have the wetsuit, they actually had better velocity. Because if you look at all of these values are all positive. So that's kind of telling you that pretty much across the board, everybody did better with the wetsuit versus without the wetsuit. So that's why we're rejecting the null hypothesis. That's why we're saying they're not pretty much equal to 0. We're saying that it should be greater than 0. Yeah. All right, but that's it for that problem. Any question for that last problem? All right, so let's do one more problem for this, and then we'll move on to independent data set. All right, so for this one, it said a listening test was administered to a Spanish teacher before and after a institutional design to improve Spanish listening skill. The maximum possible score on the test was 36. Assume that the data had a normal distribution. Determine if the institute improved listening skill at the 5% level of significance. All right. So if you look right here, they already told us to assume the data had a normal distribution. So that's it for this one. We don't have to check any assumption because we already know it has a normal distribution. So what we want to go ahead and do, we kind of want to figure out what are we doing. So if you look at it, so they're making them do this program in order to improve Spanish listening skill. So the bigger the number they get, pretty much the better they improve or the better they score on it. The smaller it is, that means the worse they did. So when should they do better? Do you think they should do better in the post-op or pre-training? So what I'm gonna do, I'm gonna do post minus pre. Because that's way if I get a positive number, that means the post did better than the pre. But if I do post minus pre, if I get a negative, that means I actually did worse in the post. So for this one, we're going to do post minus pre. So that way a positive means they did better in the post. A negative represents that they did worse in the post. Everybody go on how I'm subtracting it. All right, so let's subtract them. So this one you get -1, you get 2, you get 1, you get 4, you get -4, you get -5, you get -3, you get +3, you get 5, and you get 5. All right. Everybody get how I got the difference of these? All right. So if you look at step 2, it says, in a sentence, describe the parameter that's being tested. So for this one, the parameter that's being tested, let's say, the all right, so the parameter that's being tested is the mean difference of their pre and post test. Because we don't really care what the average of the pre and what the average of the post is. what we care about how much of a difference there was between the pre and the post. So did the score improve by like 2, 3, 5 points? Or did it actually go down by 2, 3, or 5 points? Because that's what the difference is telling me. It's telling me how pretty much how much better they did in the post or how much worse they did in the post. All right. But everybody go for number 2. All right. So let's do the null and alternate hypothesis. So for the null hypothesis, you say mu of d bar is equal to 0. The null hypothesis should always be that. Like there should never be anything other than a 0 next to mu of d bar. For the alternate hypothesis, you'll say mu of d bar and 0. So for this one, since we're trying to prove that people who took this program actually did better on the post exam, we said people who do better will get a positive value. Because if you do post minus pre, if the post is bigger than the pre, you should get a positive number. So that's why we're going to say greater than. Everybody good for the null alternate hypothesis? All right, so let's do n. So n is how many people participated in this event or in this study. So that will be 10. If we look at degrees of freedom will be 10 minus 1, which is 9. Our difference is this. All right. So by looking at my difference, did everybody who took this test or took the pre and the post test, did everybody improve when they took it in the post test? No, okay, if you look at this person right here, they didn't improve. Their score actually went down by 1 point. If you look at this person over here, their score went down by 4 points. If you look at this person, their score went down by 5 points. And lastly, if you look at this person, their score went down by 3 points. So not everybody did better. There were some people who actually got worse in the post test. All right. So up next, we're gonna go ahead and we're gonna compute the test statistic. So in order to do this one you pretty much have to just use the t-test. So you have to use the calculator. So I'm gonna go ahead and transfer over to the calculator. So first thing you go to stats, you go to edit, and I wanna delete or clear this list. So then I enter -1, 2, 1, 4, -4, -5, -3, 3, 5, 5. So that's the first thing you want to do. Enter all your data into L1, then go to stats, go to test, go to t-test, and pretty much everything should stay the same. So you say you have data because you wanted to look at L1. For mu, you put 0 because essentially you're saying there is no difference between the pre and the post. You say L1 because that's where I enter all my data set. Frequency should always be 1. And lastly, you select one of these 3. If you look at my alternate hypothesis, we say greater than. So make sure you have greater than selected and we go to calculate. So if we go to calculate, if you look at my X bar, that's D bar. So you get 0.7 for D bar. If you look over where it says S of X, that's 3.7. So that's your S of D. So we'll put 3.7 for S of D. And then lastly, if you look at your T value, you get 0.5914. So if you look at your T value, it's not that far away from 0. So it kind of telling us there is no significant difference. But lastly, if you look at P value, we actually get 0.2844. So 0.2844. This is right now. All right. But that's it for that. So we get t equal to 0.59 and we get p-value equal to 0.2844. Any question on how to get the t-value or the p-value? Yeah, I don't know why you're getting the argument level, argument error. You might want to come to me during office hour and ask me for that way I can help you, but there's really no way I can help you right now during the class. All right, so now what I'm going to go ahead and do, you go ahead and transfer over to iPhone, iPad. All right, let's see. All right. All right. So while you were gone, I fill out step number 5. So if you look at step number 5, put in the D, which is 0.7. If you look at, I also put standard deviation, which is 3.7. And I also got 0.5914, which is T-value. For this problem, we're not really using degrees of freedom. Essentially, the calculator using the degrees of freedom, but when the calculator uses it, it's just using the sample or the data, and it automatically calculated it for us. But yeah. So if you look at it, we also got t-value, which is 0.5914. And that's it for step 5. If you look at step 6, what I did, I put that this little right tail test. If you look at it, I put p-value, which is 0.2844. And lastly, if you look right here on the right-hand side where it said decision, I said 0.2844. Also, somebody already gave me the significant level, which is 0.05. Thank you. So if you look at your significant level, if you look at your p-value, which one is bigger, alpha or p-value? Yeah, p-value. So we're going to say p-value is greater. So for this one, since p-value is greater, give me a minute. Stop sharing. Here, let's try this. Stop video. Stop share. Reshare. Oh, nice. So there go our p-value, and there go our decision. So if you look at since p-value is bigger than alpha, if you look right next to it, it says fail to reject HO. So you failed to reject HO. So for this one, we'll say there is not enough evidence to say that let's see what it was again. Vanish. Let's see. Oh, all right. So for our interpretation, we'll say there's not enough evidence to say that the program helped to improve Spanish listening skill. Because if you look at the difference kind of also saying that, because if you look at it, not everybody test score improved. There are some people whose test score actually went down, which is never a good thing. Like if this program does work, we want it to work for the majority of people. Because if you look at this, it didn't work for the majority of the people. It kind of only worked for half of the people that they have, which isn't really good enough. All right, but that's it in regard to hypothesis testing for dependent data set. Any question in regard to hypothesis testing for dependent data set? Cool. So you use a t-test. Well, you use a t-test when you know population standard deviation, or if you're testing out a proportion. So pretty much you use a z-test. Pretty much for this one, you use it in 11, oh no. You use it in 10.3. All right, so up next we're gonna get into 11.3. So for 11.3, we're gonna be doing inference about two mean, but now they're gonna be independent data sets. So now the way they collected the two sample, they were independent from each other. So here is our test statistic. So in order to get our test statistic for this one, we're going to be using t distribution. But for this one, since we have two population, you kind of have to adjust this. So instead of using the regular t-test, we're going to use the one that is for two population, and I'll show you once we actually get to it. But for this one, just know this is for when you have two population. And for this one, since we have two population that we're comparing versus each other, for this one, we're not going to know the population standard deviation. We're always only going to have the sample standard deviation. So for this one, just know this one's always going to be a t distribution. All right, so let's check out the central limit theorem for this one. So if you look at the central limit theorem, the first thing it said, the sample are obtained using a simple random sample. So we first have to just know the data set will randomly select it. So normally all problem will tell you we have a random sample or we have an SRS sample. We just mean we have a simple random sample. Second thing is the sample are independent. Because remember, if the sample is not independent, then you have to do what we did for the last section, which is our dependent data set. So you have to just make sure that the way they were collecting both data sets was independent from each other. Lastly, we have to check to see if we have a big enough sample size. So to check to see if we have a big enough sample size, what we have to do, we have to check if N1 is greater than or equal to 30. But since you have two different populations, you also have to check N2 is greater than or equal to 30. So for this one, you have to just adjust it where you have to do it for both populations, not just one population. And lastly, for this one, it says for each sample, the sample size is no more than 5% of the population size. So it is going back to the big population, but usually for this one, where you're gonna skip. All right. Any question for the central limiter? All right, so let's get to the null alternate hypothesis. So for the null hypothesis, it should always be the same. It should always be mu1 is equal to mu2, because we're saying there is no difference between population 1 and population 2. The alternative is going to be saying there is a difference, because we're going to say they're not equal to each other, that mu1 is greater than mu2, or that mu1 is less than mu2. So that's how we're going to be doing the null alternate hypothesis. The null hypothesis should always be mu1 is equal to mu2, but the alternate hypothesis will be mu1 is not equal to mu2, mu1 is greater than mu2, and lastly, mu1 is less than mu2. All right. Everybody good for the null and alternate hypothesis? All right, so let's go ahead and do our very first problem. All right, so for this one, we want to do the spring break effect. So it said a statistic instructor or professor was handing out midterm grade slip on a Friday, which happened to be the day before the school spring break. He noticed that there was unusually large number of students missing from class that day, so he collected the leftover grade slip and created the data in table 6, actually table 5. Need to fix that. that summarized the midterm grade out of a possible 100 for students that attended and missed class. The professor had reason to suspect before even looking at the data that in general, students who miss class would tend to have lower mean midterm grade. Test midterm grade. Test the professor claim at a significant level of 10%. You may assume that the data for both groups are reasonably symmetric and has no strong outlier. So first thing you kind of want to notice, they say that both data come from a data set that's symmetric or reasonably symmetric. So that's another way of saying we have a normal distribution. All right, so for this one, we don't have to check it because they already told us our data set, you can already assume our data set come from a normal distribution. All right, so for this one, what are my two groups that we have? Cool, all right, so we have group number one, which is in class. So we'll say this is one, this is two. So people who were in class will say that group number one. People who missed class will say that group number two. All right. So what we want to do, we kind of want to check to see like which of these two groups did better. So that's what we're testing. So for this one, it says in a sentence, describe the parameter that is being tested. So mean test score for student who were in class and who missed class. All right, so those are the parameters that we're testing. We're testing the mean test score for students who were in class and people who missed class. All right, so let's do the null alternate hypothesis. So the null hypothesis should be pretty simple. It should say mu1 is equal to mu2. Because we're pretty much stating there is no difference between people who missed class and people who are in class. We're saying both of them score roughly the same grade. But then for the alternate hypothesis, the professor had an inclination that people who actually were in class actually did better than the people who missed class that day. So which symbol should I put to reflect that? There you go. So we put mu1 is greater than mu2. All right, so let's do this. So let's go ahead and just label everything just to kind of make that thing nice and easy. So we say 15, 80.9, and we say 11.07. This one will say 9, 68.2, 9.26. All right, so I got all of this information just by using this table. So you should be able to read a table to be able to get information out of it. But any questions so far on the labeling for part 4? All right. So what I'm gonna go ahead and do, I'm gonna do S of 1 square and S of 2 square. So I'm gonna do 11. Oops, I'm gonna do 11.07 square. And that gave me 122.54. I'm also gonna do 9.26 square and see what does that give me. So 9.26 square, you get 85.74. Well, actually 75. All right. So now we have everything filled out on number 4 to help us do part 5. Any questions so far on anything I put for part 4? All right. So you kind of know this is our standard error. And also the notation for this is usually this. All right, so if you ever see standard error or sigma x bar minus x bar 2, essentially that's what you're finding. You're finding square root of s1 squared divided by n1 plus s2 squared divided by n2. All right, so let's go ahead and do this. So let's do this in black. So we do x bar 1, which is 80.9, and you subtract that by 68.2. So we want to see what is the difference. So we do 80.9 minus 68.2. So you get 12.7. So if you look at it, you get 12.7. So that's how much of a difference we have between people who missed class and people who actually attended class. So there's 12.7. There's a 12.7 on average score difference between people who missed class and people who attended class. Up next, we're gonna go ahead and do the standard error. So it's a square root of 122.54 divided by n1, which is 15, plus s2 squared, which is 85.75, all divided by n2, which is 9. Any questions so far? How I got anything inside of that radical? All right, so let me go ahead and show you how to enter that into your TI-84 in case you ever need to calculate that. All right, so if you ever need to calculate that, you go square root, and then you go 122.54 divided by 15. And then you add that to 85.75. Divide that by 9. You press enter, and that's our score. So it's 4.21. So you get 4.21. Okay, if you round it off to 2 decimal places, it should round up to 4.21. Any question on how we get 4.21 for standard error? All right, let me take you back to my notes. All right, so if you look at it now, we have our t value. So for our t value, we do 12.7, and we divide this by 4.21. So for this one, for that way we could get a very accurate answer. We're actually gonna stop here, and we're gonna let the calculator do the rest of it for us. So to let the calculator do this information, you're gonna need all the information you enter in number 4. So let me go ahead and go to TI-84. Oh, no. All right, so on the TI-84, you're gonna go to stats. You move it over to tests. So if you remember, we're not using the t-test because instead of having one population, now we have 2 populations. So if you look at number 4, where it says 2 SAM t-test, you want to go here because this one's telling you this is for 2 population, not 1 population. So we go there, we go to stats because we don't have any data set. So if you look, it asks for X bar 1, which is 80.9. Then it asks for SO1, which is 11.07. And then you have N1, which is 15. Then you have X bar, which is 68.2. You have S of X2, which is 9.26. Then you put N2, which is 9. Lastly, what you want to do, you want to put the alternating hypothesis. So for the alternating hypothesis, we say greater than. Cool. All right, so for this one, it's going to ask you if you want to do pool. So pool means if your standard deviation are the same. So if your standard deviation are the same, you press yes. But if your standard deviation are different, you want to put no. So in our case, since our standard deviation are different, you want to put pool no. And then you have to go to calculate. But any question in regard to anything I input into the TI-84? All right, so let's go ahead and calculate. All right, so if you look at it, we get T value of 3.0. Let's just round it off to 2 decimal places. We get 3.02. So if you look at it, it's kind of telling us you do have a big difference because your T value is 3. So the reason why you say no pool, so whereas as for pool, you say no because your standard deviation are not the same. Okay, if you look at S1 and S2, they're different. So since they're different, you put that they're not pool. All right, so we get a T value of 3.02. If you look at it, you also get a P value where it says P of 0.0035. 0.0035, 0.0035. All right. So that's everything that you want from this calculator. So it gave you the T value, but it also gave you the P value. So I'm going to go ahead and transfer over to the notes, and we'll kind of go over what did I input on the notes while you were gone. All right, so while you were gone, I entered the T value. So the T value 3.02. So yeah, that you're telling me how much of a difference do we have? I also enter all of step number 6. Well, not all of it, but most of it. So if you look at step number 6, I put that this is the right tilt test because we put the right arrow. If you look at it, I put p-value, which is 0.0035, and I also put p-value again at 0.0035. So if I go back and look for the alpha, I should find that alpha. If you look at it, they say alpha or significant level is 10%. So that's my alpha level. They put 0.10. Everybody get p-value of 0.0035 and alpha of 0.10. Cool. All right, so for this one, should I reject or should I fail to reject? There you go. So you should reject. Because you reject because alpha is bigger than p-value. So since alpha is bigger than p-value, we'll say there is enough evidence to support the claim that student who attended class prior to spring break All right, and that's our conclusion. All right, so if you look at my conclusion, I said there is enough evidence to support the claim that student who attended class prior to spring break did better than a student who didn't. Which makes sense because if you look at it, since you had that big gap between the mean of student who attended class and the mean of the student who didn't attend class, you can see that there's a big difference between the two of them. So that's why we say there's enough evidence to conclude that people who attended class prior to spring break are doing significantly better than people who didn't attend class. And that's it for that problem. Any question for that last problem? All righty then. All right, so let's do the second one. So for the second one, it says quiz timing. A young statistics professor decided to give a quiz in class every week. He was not sure if the quiz should occur at the beginning of class when the students are fresh or at the end of class when the student gotten warmed up with some statistical thinking. Since he was teaching two sections of the same course that performed equally well on past quizzes, he decided to do an experiment. He randomly chose the first class to take the quiz during the second half of the class period late, and the other class took the same quiz at the beginning of their hour early. He put all of their grade into a data and found the mean and standard deviation for both group and put it in table 6. Test to see if it make a difference when the quiz was given during the class with a significant level of 20%. All right, so let's get started. All right, so if you look at this one, for this one, let's say, what are my two groups? Cool. So late and early, perfect. So we're gonna say this is group 1, we're gonna say this is group 2. So if you look at it, they're independent from each other because it's kind of impossible for a student to be in both class. So when I'm randomly selecting from one class, that's one population. When I'm randomly selecting for another class, that's the second population. So pretty much you're either in one population or the other population, but you can't be in kind of both populations. So for this one, if you look at it, they don't tell me anything about our data set being normally distributed. So what we have to do, we're gonna check the central limit theorem. So for the central limit theorem, all we're gonna check to see if we have a large sample size. So let's check if we have large sample size. Cool. So one thing you have to kind of realize for this one, since this is for the mean, since we're testing the parameter of the mean, you have to check to see if N1 is greater than or equal to 30 and if N2 is greater than or equal to 30. So for this one, if you look at N1, N1 is the sample size of the late class. So that's 32, which if you look at 32, 32 is indeed bigger than 30. Then you have to do N2, which N2 is the early class. So you go 30 is greater than or equal to 30. So that one also checks out because 30 is indeed greater than or equal to 30. So that's our large sample size. So since this condition checks out, we're gonna say our data set is approximately normal. All right. Everybody get why our data set is approximately normal? All right, so let's do step 2 in a sentence. So it says, in a sentence, describe the parameter that is being tested. So the parameter that is being tested is the mean quiz score for students taking the quiz late and early. So we're testing the mean quiz score for student taking the quiz late, which is they take it at the end of class, or student who take it early, which they take in the beginning of class. All right. Everybody good with step 2? All right, let's do step 3. State the null and alternate hypothesis. So the null hypothesis pretty much just state that there is no difference between the two. So the mean quiz score for the student who take it early should be the same as the mean quiz score for student who take it late. So that's what the null hypothesis is stating. There is no difference between the two then. The alternate hypothesis stating there is a difference. So for this one, do they kind of make it clear cut who do they think will do better, or do they kind of just say we just want to prove there's a difference? Yeah, just a difference. So we'll say mu of 1 is not equal to mu of 2. Everybody go for the null and the alternate hypothesis. Oh, everybody is perfect. All right, so let's do where we fill this out. So we do N1. N1 is 32, 30, 22.56. Cool. If you look at this, my standard deviation are not the same. So for this one, when I ask for pool, you're going to put no, because the standard deviation are not the same. The only time we say there are pool is both of the standard deviation are the same. So lastly, I want to do S1 squared. So you do 5.13. So you get 26.3169. And then I'm going to do 6.61 square, 6.61 square. You do 43.6921. All right. And that's it for step number 4. Any question for step number 4? So let's go ahead and do x bar 1 minus x bar 2. X bar 1 minus x bar 2 is 22.56 minus 19.73. So unfortunately, I'm pretty sure I'm going to run out of room. So you go 22.56 minus 19.73. This is equal to 2.83. So the difference between the two of them is 2.8 points. So that's the difference between the two quizzes, between the late, people who took it late, and people who took it early. Now we're gonna go ahead and do, we're gonna do standard error. So it's a square root of 26.3169 divided by N1, which is 32, plus 43.6921 divided by 30. All right, so let me go ahead and do that on the TI-84. All right, so for the TI-84, we go second, radical. You go 26.3169. You divide that by N1, which is 32, plus 43.6921, and you divide this by 30. If you do that, you get roughly 1.51. So I say 1.51. So to get our t value, we're going to do the difference, which is 2.83 divided by 1.51. So let's go ahead and do this. All right, so for step number 5, here are some of the things I put. I put the difference at 2.83. I put the standard error is equal to 1.51. And then T is equal to 2.83 divided by 1.51. So in order for me to get a very accurate answer, I'm going to let the calculator do the rest of it for me. So the calculator is going to give me what is the t value equal to, but it's also going to give me the p value. So I'm going to go ahead and transition over to the TI-84. So for the TI-84, we go to stats, we go to tests, and we're going to do number 4, which is a 2-sample t-test. So for x bar of 1, we got it to be 22.56. Standard deviation of x is 5.13. And 1 is 32. X bar is 19.73. S of x is 6.61. And then the sample size for the second population is 30. All right, so if you remember for this one, we put not equal to because we just want to prove there's a difference between the two of them. And if you remember, we say it's no pull because the reason why it's not pull because you don't have the same standard deviation. So now I go over to calculate. All right, so if you go to calculate, you get t value is equal to 1.874. Also, if you look at p value is 0.0662. So the two main things that I got from here is the t value, which is 1.87, but also the p value, which is 0.066. Any question on how I got the t or the p value? All right, so let's go back to my notes. All right. So this is the only thing I put. For number 5, I put what the t value is. So the t value is 1.874. But also for the p value, I put that this is a two-tailed test. I put the p value, but since I ran out of room, I wasn't able to put it there. And I put the p value here. If you remember for this one, the alpha for this, yeah, my alpha was 0.20, but let me double check my calculator. Twenty-two point five six. Standard deviation is 5.13. Yeah, I don't know why it's giving you that. You might want to check back on your number because your number are more likely something is off with your number. Just go back and just look at your number. You probably put pulled yes versus pull no. Okay, you want to make sure that where it says pull, it should say no, not yes. So you look back on what you entered. All right, so we got the t value, which is 1.874, but you should have also gotten a p value, which is 0.0662. So the alpha level for this one that they gave us in our problem was 0.20. So if you look at 0.20, if you look at p value, 0.20 is clearly bigger than 0.066. So we select p value is smaller than alpha. So since p value is smaller than alpha, you reject the null hypothesis. So in this case, since we reject the null hypothesis, we'll say there is a difference between So but there is a difference between quiz scores that are given early in the class versus late in the class. So since we did reject, we're stating there is a difference between whether they give the quiz in the beginning of the class or whether they give the quiz at the end of the class. So it does make a slight difference. All right, but that's it for that second example. Any question for that second example? All right. So the last section for chapter 11. So the last section for chapter 11 is going to be inference about two population standard deviations. So we already did the inference of two population proportion. We already did the inference of two population mean. So the last one that we are left to do is pretty much the inference about two population standard deviation. So just know for the inference of two population standard deviation, it has two requirements. One of them is that the data set has to come from a simple random sample. The other one, the population, is from a normally distributed data set. But if it's not normally distributed, what you could always do, check the central limit theorem. And based off of the central limit theorem, if your sample size is big enough, then you can say it's approximately normal. So if they don't tell you the data set is normally distributed, you could always use that as the backup plan. All right, so for this one, we are going to be using something called an F-test. So the F-test is actually a distribution. And for this distribution, it relies on degrees of freedom. So for the degrees of freedom, you're actually going to have 2 degrees of freedom. You're going to have degrees of freedom on your numerator and degrees of freedom on your denominator. So pretty much if you always put population 1 on top, n of 1 will be the degrees of freedom for your numerator. If you do s of 2 on the bottom, then your degrees of freedom for the denominator is going to be n2 minus 1. So the degrees of freedom always reflect pretty much whatever s value, which is the sample standard deviation, you put on top or you put on the bottom. If you put s2 on the top, then essentially what's going to happen, the degrees of freedom for the numerator will be n2 minus 1. Everybody good so far for the F distribution? And just know for the F distribution is non-symmetrical, but as your degrees of freedom get bigger and bigger, it becomes more and more symmetrical. Right, so let's go down here. All right, so to kind of illustrate that, here's a drawing. So if you look at it, if you have degrees of freedom of your numerator is 1, and the degrees of freedom of your denominator is 1, is the blue one. So if you look at that, that's pretty skewed to the right. But now let's say here's the red one. Say you have a degree of freedom of 5 for your numerator and a degree of freedom of 2 for your denominator. If you look at this one, this is the red one over here. If you look at it, it's still skewed to the right, but if you kind of look at it, it's kind of moving more to the right-hand side, so becoming a little bit more symmetrical. So say if you look at this next one, well, not the next one, but if you look at the middle one, you see the degrees of freedom of numerator is 100, and the degrees of freedom of denominator is 100. And that produces this one over here. So if you kind of look at that one is symmetric or approximately normal. So same thing goes just like with the chi-square distribution. The bigger the sample size you get, the more and more closer it should become a normal distribution. So that way we apply the central limit theorem for this one. And remember, usually the rule of thumb for this one, if n is greater than or equal to 30. So some characteristic about the F distribution. If you look at the F distribution, it is not symmetric. The F distribution is skewed to the right. If you look at the second bulletin point, it says the shape of the F distribution depends upon the degrees of freedom in the numerator and denominator. This is similar to the chi-square distribution and the student t distribution, whose shape depends upon the degree of freedom. Third bulletin point, the total area under the curve is 1, the value of f are always greater than or equal to 0. So are you saying it should always start off at 0? And it's pretty much you're going to keep going to infinity. All right, so those are some key characteristics of the f distribution. And for this one, you can just ignore this because we're not doing the critical value. Essentially, we're going to be doing the p-value method. So don't worry about how to get that. Right. So let's get into this. So if you look at the null and the alternate hypothesis, they're the same as before. The only thing changing, instead of having mu, we're changing it to sigma. So we're saying sigma 1 is equal to sigma 2, which just means that the two standard deviations of those populations are similar to each other. If you look at where it says the alternate hypothesis, which is H1, it says sigma 1 is not equal to sigma 2, or it says sigma 1 could be greater than sigma 2, or sigma 1 is less than sigma 2. So that's going to be your null and your alternate hypothesis. So it's either going to be a left tail, two tail, or a right tail test. And finally, our test statistic. This is probably going to be the simplest test statistic. It's just equal to SO1 squared divided by SO2 squared. So that's how you're going to find the test statistic. You divide the standard deviation square of the first population divided by the standard deviation square of the second population. Everybody good for that so far? All right, so let's go ahead and do some problem. All right. So for this one, it's gonna be a very basic problem. So for this one, I already told you the null hypothesis is sigma 1 is equal to sigma 2. My alternate hypothesis is sigma 1 is less than sigma 2. Cool. So for this one, say check for assumption. So for this one, we don't have to check for assumption. Why do I not have to check for any assumption? Cool. Yeah, if you look right here, it says assume that the population are normally distributed. All right, so that's why we don't have to check any of the assumptions because it says assume that the population are normally distributed. All right, so for this one, in a sentence, describe the parameter that's being tested. Well, you can put the standard deviation because if you look at this one, I don't really give you any backstory or any context of this one. It's a very plain problem. All right, so let's do step number 4. So for step number 4, we want to get SO1. So SO1 is 15.9. SO2 is 23. So I'm going to get SO1 squared. So that's 15.9 squared. So that's 252.81. Then we're going to do 23 squared. And you get 529. Any question? I got SO1 square and SO2 square. All right, so then I forgot to put N1 and N2. So if you look at N1, they tell us the sample size of 21. If you look at N2, sample size of 26. So for this one, if I want to calculate the F value, it's pretty simple. I get SO1 squared, which is 252.81. And you divide this by SO2 squared, which is 529. So if I go ahead and do this, 252.81. You get 0.4779. All right, so that's your F value. So if you look at this one mathematically, it's not that hard to do because the formula is very simplistic. All you have to do is get the sample standard deviation of your first population, square it, divided by the sample standard deviation of your second population, and yes, remember to square. So up next, we're going to go ahead and do the p-value. So for this one, if you look at the p-value, this is a left tilt test. So that means we're going to be getting this value over here. So I'm going to go over, and we're going to do this in the TI-84. All right. So for the TI-84, let me clear this. You want to first go to stats. You want to go to tests, and actually hit the up button. And you want to do right here where it says 2 sample F tests. So we're going to do 2 sample F tests. So if you look at it asking for data or they're asking for stats, since we don't actually have any data set to give us all the stats, you leave it as stats. So I'm going to say standard deviation of X1 is 15.9. N1 is 21. Standard deviation of X2 is 23. Sample size of that second population is 26. If you look at it, we say it was less than, so we go to calculate. But any questions so far, anything I enter into this calculator? All right, so let's go to calculate. So if you look at it, give me the F value, which is 4.779, which we calculated by hand because it wasn't that bad to do. If you look at it, they gave me the P value, which is 0.04801, 0.04801. All right. Everybody good on the P value 0.04801? All right. So back to my notes, I shall go. All right. So if you look at it, well, they didn't give me an alpha. So for this one, since they didn't give me, oh, sorry, they did give me an alpha. Alpha is 0.10. There you go, 0.10. So if you look at alpha, if you look at p-value, alpha is clearly bigger than p-value. So you want to reject the null hypothesis. So since we reject the null hypothesis, we'll say there is enough evidence to say that sigma of 1 is smaller than sigma of 2. You can either get it manually or with the calculator, like manually or with the calculator, like you should be able to get the same thing since you just have to do S1 squared divided by S2 squared. So it shouldn't really be a difference if you do it with the calculator, if you do it without the calculator. All right, but any question in regard to that first example? So let's go on to this second example. All right, so for the second example, same thing. We're not going to do it with the context. Where you're going to do it with the data set. So let's go ahead and do this. All right, so if you look at this one, they already told a null hypothesis is sigma 1 is equal to sigma 2. If you look at the alternate hypothesis, they say sigma 1 is not equal to sigma 2. And also, if you want, we could just start doing everything else. So we could start putting N1 and N2. So you can say N1 is equal to 21. N2 is equal to 21. SS is equal to 8.6. S2 is 9.2. 9.6. Oops, 8.6. Where is 73.96. 9.2 square is 84.64. So for this one, if you look at it, you don't have to check for assumption because you already told it the distribution is normal. So right here, you just want to tell them we're testing the parameter of standard deviation. So let's go ahead and do this one. So if you look at part 5, we want to compute the F value. So to compute the F value, we get 73.96 divided by 94.64. So what the F value is calculating to see is there's a significant difference between the standard deviation of these two different populations. So if you do 73.96 divided by 94.64, you get 0.7815. Everybody good? I got 0.7815. All right, so then to get the p-value, that this could just happen by random chance. Oh yeah. All right, so this is a little typo. I put 94 right here. Should be 84. Thank you for that. So we do 73.96 divided by 84.64. All right, so you get 0.8738. So that's our F value. Everybody good with the F value? And just remember for this one, if you look at the alternative hypothesis, it says not equal to. So that means we're gonna put not equal to. So this should be a two-tailed test. So let's go ahead and go to the calculator to do this test. So we go to stats, we'll go to test, actually go up, and we'll do the two sample F test. All right, so for stats, we'll put SO1, which is 8.6, N1, which is 21, S of X of 2, which is 84.64, N2, which is 21. And then make sure you put not equal to, then go to calculate. $73.96. Ah, 9.2. Here, something I did wrong. What did I do wrong? I go right here. Okay, yeah. So if you look at standard deviation for population 2, I put 84.64, which is completely wrong. Should have been 9.2. So yeah, so you be careful. So you go calculate. But luckily we had already calculated, so we kind of knew our calculator was wrong. All right, so if you look at the F value now, it's 0.8738, which is what we got. But now if you look at the P value is 0.7659. So you get 0.7659. And if you look at it, you have an alpha of 0.10. Let me go back to my notes. All right, so if you look, I put the F value right here. I put the P value right here, I put the P value right here, I put alpha over here. So if you could look at my P value and my alpha, this is my P value 0.7659 and my alpha 0.10. P value is bigger than alpha. So in this case, you say fail to reject. So we'll say there is not enough evidence to support the claim that sigma 1 is not equal to sigma 2. So for this one, we're stating there's not enough evidence to say there's a significant evidence between sigma 1 and sigma 2. And that's it for the second example. Any question for the second example? So quiet today. All right, so let's do an actual word problem. So for this one, say walking in the airport. So it says researcher Seth B. Young measured the walking speed of traveler in San Francisco International Airport and Cleveland Hopkins International Airport. The standard deviation speed of the 260 travelers who were departing was 53 feet per minute. The standard deviation speed of the 269 travelers who were arriving was 34 feet per minute. Assume that the walking speed is normally distributed. Does the evidence suggest that the standard deviation walking speed is different between the two groups using the alpha 0.05 level of significance? I guess the sun sucked all of your energy away. All right, so for this one, if you look at the problem, since they tell us assume the walking speed is normally distributed, let's check out this assumption. So we could say we have a normal distribution. So for this one, we don't have to check anything because essentially we already know it's normally distributed. All right, so if you look at it, what we want to do in step number 2 is write a sentence to describe the parameter that is being tested. If you actually look right after that, it says, does the evidence suggest that the standard deviation walking speed is different between the two groups? So we're testing the standard deviation walking speed for these two groups. So we'll put that. The standard deviation. All right, so that's step 2. So step 2, it says the standard deviation walking speed for both groups. So that's what we're testing. So if you look at the null hypothesis, we put sigma 1 is equal to sigma 2. But for this one, we have to say who's sigma 1. So for sigma 1 or population 1, we're going to say these are people in San Francisco. So for population 2, we're going to say these are people in Cleveland. So those are my two population, people who live in San Francisco, or sorry, people who are in the San Francisco airport or people who are in the Cleveland airport. So for the null hypothesis, we're going to say sigma 1 is equal to sigma 2. So the two standard deviation of those two groups are the same. My alternate hypothesis, so what am I trying to prove? I'm trying to prove that people in San Francisco standard deviation walking speed is less than, or yeah. So we just want to prove it's not equal to because it says different. So up next, let's go ahead and calculate this. So for S1 is equal to, so the standard deviation for San Francisco is 53. And the standard deviation for, oh, actually, I got this wrong. They were for departing and arriving. So yeah, so my two group are departing and arriving, not San Francisco or Hoskins. That's just the airport they went to collect this data set. So that shouldn't affect my alternate hypothesis. Luckily, we did the right alternate hypothesis. So for the standard deviation for people arriving was 34. So I'm gonna go ahead and find SO1 square and SO2 square. So we'll do 53 to the second power. That's 2A09. And then we'll do 34 square, which is 1156. All right, so that's SO1 square and SO2 square. Finally, we're going to do SO1 square, which is 2,809, all divided by 1,056. So let's go ahead and see what does that give me. 2A09 divided by 1156. So you get 2.42993096. All right, so that's my F value. So for this one, you can kind of clearly tell like if the F value that your calculator gives you is a little bit off, because this one we should be pretty accurate. So now we're gonna go ahead and do is go ahead and do this in the TI-83. Oh, 84. All right, so we go on, we go to stats, we go to tests, and we'll do a F test. Where's my F test? Oh, so two sample F tests. So if you look at here for SO1, we said it was 53. N1, it was 260 people. For SO2 was 34 for the standard deviation, and that one had a sample size of 269. All right, lastly, if you remember, we put not equal to, so let's keep the trend going, not equal to. Let's go to calculate. All right, so if you look at the F value, the F value matches the F value that we got. So the only thing we're actually looking for is the P value. So if you look at the P value, it gave us to us in scientific notation. So that's 0.002845678910. Pretty much we get 0.00000000001. So practically it's telling us that our P value is pretty much non-existent. It's almost equal to 0. Yeah, you should be pretty sure P alpha should be bigger than this. Good. All right, so my alpha, really alpha doesn't matter. If P value close to 0, kind of telling you it doesn't matter. So alpha, which is 0.05, and let me transfer you back to the notes. I forgot to transfer you back. All right, so if you look at my p-value practically equal to 0, but my alpha is equal to 0.05. So 0.05 should be bigger than 0. So for this one, you want to reject this. And for our conclusion, you want to say there is enough evidence to support the claim that All right. There is our conclusion. So the conclusion is there is enough evidence to support the claim that the standard deviation walking speed for arriving is different than departing. Should be that, not forward. All right, and that's it for that last problem. Any question in regard to the last problem? All right, so we're gonna do our final problem in this chapter, and then we'll go on to chapter, well, we might go on to chapter 12. We'll see how we feel. So let's do this last one. So it says a filling machine, a quality control engineer wants to find out whether or not new machine that fill bottle will, lost my place, fill bottle with liquid have less variability than the machine currently in use. The engineer calibrate each machine to fill bottle with 16 ounces of liquid. After running each machine for 5 hours, she randomly select 15 filled bottles from each machine and measured their content. She obtained the following result. Right. So for this one, so we have these two machines. We have the old machine and we have the new machine. So what we want to do, we want to prove is there's a significant difference between the old machine and the new machine. But in order to test their difference, what we want to do, we want to test their variability. So whenever they say variability, that means standard deviation. Okay, if you kind of remember all the way from chapter 3, when we first introduced standard deviation is a way to pretty much to measure variability. So if something has variability, the best way to measure if it has variability is by its standard deviation. So for this one, what are my two populations? What? All right. So my two populations are the old machine and the new machine. There you go. Perfect. So those are my two populations. So I'm gonna say the old machine is 1. I'm gonna say the new machine is 2. So if you look in the bottom, there's a sentence that says, is the variability in the new machine less than the old machine at the alpha equal to 0.05 level of significance? No, the normal probability plot indicates that the data are normally distributed. So if you look at this one, we already know that normally distributed. So for this one, no need to check assumption. And if you look at this one, I pretty much gave you a box plot. So if you look at both of the box plots, so remember, variability or standard deviation measure how spread out they are. So if you look at the new machine, if you look at the old machine, are both of them the same spread or is one more spread out than the other? Yeah, so if you look at the old machine is more spread out. Cool. So that's what we're going to be testing right now. We're going to be testing to see if this spread, if this is a significant spread to say like, okay, we should get the new machine because the new machine have a significantly smaller spread than the old machine. All right, everybody go with that? All right. so let's go and do step 2. So in a sentence, describe the parameter that's being tested. The standard deviation for O and new machine. All right. So the null hypothesis should be very straightforward. Sigma 1 is equal to sigma 2. The alternate hypothesis, that one might be a little bit trickier. So which machine do we think should have the smaller standard deviation? Machine number 1, which is the new machine, or machine number 2, which is the old machine? Yeah, so we think the new machine should have a smaller standard deviation, so we should put less than. Everybody good on less than? Sweet. All right. So let's go ahead and do this. So for step number 4, unfortunately, we can't do step number 4, because if you look at it, they only gave us the data set. So what I had to do, I had to enter this data set into TI-84 or into the TI-84. So that's what I'm gonna go ahead and do right now. I'm gonna enter this data set into the TI-84. So let's do TI-84. Let's turn it on. Let's go to stats. Let's go to edit. Let's go to clear this. Cool. All right, so I'm gonna enter the first data set. So 16.01, 16, 16.04, 16.10, 15.2. All right, so that's my data set for L1. Now we have to do L2. So for L2 is 16.02, 15.95. Cool. All right, so I entered all of my data into L1 and L2. So that's probably gonna be the hard part. Then you go to stats, you go to tests, you go up, and you go into 2 sample F test. So for the 2 sample F test, you click it. For this one, you don't want to hit stats because remember, you don't have any of this. You want to go to data and you want to tell the calculator to get this information for you. So if you look at L1, or list 1 should be L1, list 2 should be L2. So when it says list 1, it's saying population 1. When it says list 2, that means population 2. So for us, if you look at our alternate hypothesis, we said it should be less than. So we'll put less than. So then we go ahead and press calculate. Cool. All right, so if you look at our F value is 2.73686, whatever. So that's my F value. If you look at my P value, okay. All right, so for this one, I did a mistake because if you look at Sigma 1 is actually my old machine, and Sigma 2 is actually my new machine. So what I told it right now, I told him that the standard deviation of the old machine should be smaller than the standard deviation of the new machine. So I actually chose the wrong alternate hypothesis because I actually didn't pay attention to the labeling. So pay attention to the way you label. So all I have to go ahead and do here is change that to greater than. And we go to calculate. All right, so now that's like more reasonable. So if you look at my p-value, we get 0.0348. 0.0348. 0.0348. All right, but any question on p-value 0.03 or f value of 2.73? All right, so let's go ahead and go back to the notes. So if you look at it, I put p-value and my f value. So if you look at p-value 0.0348, if you look at alpha 0.05. So if you look at alpha, alpha is clearly bigger than p-value. So you press this one, so you reject. They state there is enough evidence to support the claim that the new machine standard deviation is smaller than the old machine. All right, so we'll put there is enough evidence to support the claim that the new machine standard deviation is smaller than the old machine. Yeah, there should be an option for your calculator. Try talking to me during my office hour, and I'm pretty sure I should be able to find it. All right, but that's it in regard to this last problem. Any question for this last problem? Cool. All right, and we're all done with chapter 11. All right, so what that mean for tomorrow? Tomorrow we're gonna go over chapter 12. So here, let me stop share. Oh, so just remember, for test correction will be due tomorrow. Let's see why I can't. Let's just do that. Yeah, so test correction, they'll be due tomorrow. So if you still haven't done your test correction, do get the test correction done as soon as possible. I also sent out an announcement with the final exam topic. So you do kind of want to go over it. So if you go to announcement, then you go to topic for the final, click right here, and it should give you all of the topic that should be covered on the final. But remember, like I said, 80% of the final It's gonna be chapter, what is it, chapter 10 and up. So chapter 10 and up. You forget about those percentage. I accidentally put in there, but shouldn't be there. So like 90% or 80% of the final is gonna be these three chapters. So you do want to focus on these three chapters, and the final chapter is gonna be tomorrow. And also just remember, you do have a quiz tomorrow on what we learned today. So you do kind of want to make like a, pretty much have like a sheet of paper to have all of your notes ready for tomorrow. So that way, any question I ask you, you should be able to answer it. But pretty much we're almost done. We only have technically tomorrow the last lecture day, and then Wednesday is for any question you might have for the final. And then Thursday, there is no class because pretty much you're gonna be taking the final that same time. So you're gonna have from 7:30 p.m. all the way to 9:35 p.m. to do the exam on Thursday. All right. So that's pretty much it for today. I'll start dropping the quiz right now. I'll put in the thing that said to drop the quiz. Well, the final should be missing because well, you haven't taken the final. So for homework set number 4 is gonna be pretty much all of the homework for chapter 9, well, all of the homework for 10, 11, and 12. So all of the homework for 10, 11, and 12, that's gonna be your last homework set. So homework set number 4 is gonna be you turning in the work or the homework for chapter 10, 11, and 12. Any other questions? Yeah, Thursday. Yeah, due on Thursday. Everything is pretty much due on Thursday. The homework is gonna be due on Thursday. The tests are gonna be on Thursday. And also just remember for the final is, well, pretty much there is no test correction for the final. So please do not ask if you could do a test correction on the final. The final is the final. So there's no more for the final. Yeah, it kind of depends how much I get through tomorrow. For sure, you have to do 12.1, and depending on how much I go through tomorrow on 12, you might not have to do 12.2. Like, I'm pretty confident I should be able to finish 12.2 tomorrow, but we kind of just go with the flow with it. Right. Any other questions? All right, so pretty much I'm gonna just end this meeting for that way I could start uploading the notes that I went over today, and I also could upload the video. You're welcome. Have a great night.